that we have a metal sphere with radius A and with free charge Q, which is capital Q. This is how we denote this. It is surrounded by a region which has some permittivity epsilon, which is given over there. The question is to find the potential at the center of this metal sphere. Now, whenever we want to find the potential at any point, the best reference that we do have is, we know that if we have a charge somewhere here, if we have some charge here, the only point that we know is the infinity. So it's this point, which is equal to 0, because it's too far. So this charge, it produces 0-volt potential far away. So since that is the only point of reference, what we need to do, we need to calculate the potential difference, which will be, in this case, which will be equal to V0 minus V infinity, okay? With a minus sign, all of these terms have a minus sign. So V0 minus V infinity, but since V infinity is equal to 0, you can also write V0, right? Which is the potential right at the center. So as we are coming from infinity closer to this object that we are analyzing, we have the same behavior for the electric field from infinity to B. Nothing is changing. So this integral should be from infinity to B plus the integral from B to A, because from B to A, the electric field inside, it preserves, it has the same way of behaving. And then we have to integrate from A to 0, okay? So this is what we should be doing. But in order, so apparently, to find the potential, we need the electric field. And to find the electric field, we can use a Gauss law. Let's try to use the Gauss law. Initially, let's assume that the radius, let's analyze the region where R is smaller than A. If R is smaller than A, that means that we are inside this metal, okay? So this metal structure, inside the conductor, the electric field is equal to 0. The electric field intensity, it will be equal to the electric flux density, and this will be equal to the polarization inside the metal. So this was easy. When we say easy, it's easy for us because if we substitute later on a 0 here, that means that this term will not contribute anything to find the potential difference between point A and point 0. It is also reasonable because conductors, they are equipotential. So if we have an object which is a metal, like this object that I'm having in my hand, or this, I cannot extend it too much, this will be equipotential because it's a conductor. So potential difference will be 0. Let's pick another region, and let's assume a region where R it is larger than A. If R is larger than A, we can write the following: the integral of dds, this was equal to Q. And here we can say that d, from here we can say that d times 4 pi r squared, this is Q, and the electric field flux density would be equal to Q over 4 pi r squared. Okay, so this is the d, and from here we can say that using the relationship, the d is equal to permittivity times the electric field intensity. This can also be written as epsilon 0 E plus the polarization, and yes, this is all we can say. We can also describe the polarization as, let's do it like this. This is epsilon 0 E plus epsilon 0, the susceptibility times E again, and that and this term here, this is the relative permittivity or dielectric constant, and this is epsilon E. So the epsilon of a medium is always equal to some constant times epsilon 0. Okay, so this is the expression for D. If this is the expression for D, then we can say that the electric field E is equal to Q over 4 pi epsilon over r squared whenever radius is between A and B. Okay, so if we are in this region, which we denote from A to B, this will be the electric field. But the electric field outside of the region, this will be equal to 4 pi over epsilon 0 r squared. This is when r is larger than b. So we are talking now, when r is larger than b, we are talking about this expression, or when we are out there. So we have this expression where we have the epsilon 0. If we are inside this medium, the expression of the electric field, it will be simply modified by this epsilon, because the electrical properties of the medium, they are different from vacuum, they are represented by the permittivity. So these are the electric fields, and these two expressions, we can deduce them from this single d. The only thing we have to figure out is that we see that the d is different, it's independent of the properties of a medium, okay? This vector d, and then we get these. So what is left is that we simply need to integrate the following terms. So here we have E from minus infinity to B. This will be, actually, this is a constant, so we can take it like this. The constant, if we can take it out, Q over 4 pi from minus infinity to B. We have what? We have this one, right? Because it's vacuum. So we have also 1 over epsilon 0 integrating 1 over r squared dr from infinity to b. That's good. Plus the integral of this electric field. So we can factor out again q over 4 pi times 1 over, sorry, it's not 0, 1 over epsilon integrating from 1 over r dr. So this is all that we need. And then this will be then equal minus. So in this case, well, let's find this integral. This is minus 1 over r, right? So this is minus 1 over r. And by the way, let's write this for both integrals. They will be minus 1 over r. The limits of the first integral, they will be from infinity to b. From infinity to b. So this will be equal to 1 over r from b to infinity. Okay, so we take the minus inside. And by the way, actually, we can do it also like this. Okay, so we can do it. We can. I was just assuming. So they both come out with a minus. Since we have another minus, they can cancel out because we get a plus. But let's forget it for now. So this will be equal to 1 over infinity. This is 0 minus 1 over b. What is this? Sorry, this is r. So this is equal to minus 1 over b. We found this. And then we have also the integral of minus 1 over r, integrating from, what was this? From b to a, right? So we have not written this here, this would be b to a. So if we integrate this from b to a, this will be equal to 1 over r from a to b, which will be equal to 1 over b minus 1 over a. So we need to include these expressions in here. So we have a minus sign, and we can factor out q over 4 pi. We can insert this minus sign inside. This is 1 over epsilon 0 times, if we insert a minus sign here, this will be minus 1 over b, it will be 1 over b. Plus 1 over epsilon times this term, but since we have this minus sign at the front, we're going to change the expression. So this would be 1 over a minus 1 over b. So this is the answer. The potential in the center is equal to this. Okay. 1 over epsilon 0, 1 over b. Yeah. Now, is it clear so far? So we found the potential, everything was good. One thing that we can add here is that we can try to determine what is the polarization. So here, the polarization out here is equal to 0. Okay. The polarization inside the metal plate is also 0. So we have no polarization here also. So P is equal to 0. The only polarization is going to be in this region here. And to find the polarization, we have we can write down this expression here, which will be as such: the polarization is equal to epsilon 0 times psi e times the electric field. But the electric field in consideration is the electric field in the region between A and B, which is this. So this will be equal to epsilon 0 psi e, substituting for Q over 4 pi epsilon over r squared. So this will be the polarization. We know all three polarizations. Inside the metal, the conducting metal is 0. In this medium, it is given by this expression, and out there is still equal to 0. Okay. D, it has the same expression all over, starting from this region outwards. D will be the same. Any question for this problem? Okay. Now, from here, you can assume this one as a homework. You can try to determine what is the induced charge because of this non-zero polarization on the surface, which is going to be here to P dot AR, because this is the normal component. And we can also assume what is the charge density because of the polarization on the volume, which is going to be equal to the divergence of the polarization vector.